All right, so start of a new unit. So move from foraging to social foraging, so starting to add some of that social complexity things in. So reminders here, so now that's this unit, we just have these two G1 and G2, so we'll be done with this unit this week. So there's this upcoming Sunday, we've got a reading assessment as well as a comprehension exercise that are due this Sunday. Otherwise, at the end of the week, due Friday, then it's this 1 to 2 paragraphs from your group. So only one person from your group has to upload it because it's a group assignment. So as long as one person uploads it, then that score will go to everybody in the group. So identifying the animal that you're studying on, the relevant context that is motivated by possible anthropogenic effects. So that helps us then give you feedback on whether this makes sense for the final project. And then we can get you that feedback and you can move along your way. Try to, no zoos and no pets. So no animals in captivity is the idea here. Looking for kind of general animals of the Southwest that you conceivably, if you were to run an experiment, propose an experiment and get funded, that you could go off somewhere in Arizona-ish area and then do that study there. So that's kind of the idea. If for some reason there's a group member who you joined the group together, but you haven't been able to get in contact with them or they're not participating, but everybody else is, then you can elect to leave their name off the report. And then that will then trigger an investigation to say, well, is this person, do they, what's going on there? And then do they, they deserve a 0 and everybody else deserves the grade and so on. So if there are, hopefully there won't be those issues, but if those issues do come up, as they sometimes do, then the easy way to do that would be to leave the name off the report. All right, any questions? Okay. All right, so group foraging. So this is the reading assignment for this week. It's this, so I'm going to talk a little bit about it, but there'll be more details on perusal. And in this particular case, they had these bats, these greater mouse-tailed bats, and they designed a little device that they could attach to these bats. And these could do GPS logging, so they could keep track of the position of these bats as they're foraging. But then it also could record the sounds of their calls and the sounds of things around them. So they could actually get the calls of these bats as well as the calls of bats around them. And they were trained so that you could actually differentiate between calls that were for certain purposes and calls that for other purposes. So they were able to sort of keep track of bats as they fly around. And then these different flags here, they could tell when they made an attack on some prey. These particular bats like to attack these carpenter ants. They find these aggregations of carpenter ants and then they swoop in and eat them. They also will run into conspecifics, other bats foraging. So they were able to study how these bats flew around, how often they were making attacks, which we assume were successful, and then how often they interacted with conspecifics, how often they interacted with others, and how their spatial position relative to conspecifics affected how often they would make attacks. So it allowed them to see how the social environment modulated their foraging experience. And so these are some of the things that they found. So back to here. I think I've clicked on the paper by accident, so sorry about that. So I do try to make it so that these things are clickable, so in case you do want to read more about these things. So what they found, for one, so what we see here in this graph is the black line is if you just look at the spatial position from where these bats were, you can kind of build a model that predicts the if they ignored conspecifics but had sort of a similar spatial expanse, or if you kind of like, where the food locations are, and if they kind of hung around those food locations, but in the model, they fly right through other bats. They aren't attracted to them. They aren't repelled from them or anything like that. Then what would be the kind of null hypothesis? What would be the time that you'd expect them at different densities? And so over here, they have estimated density from nearest conspecific. And so from no distance, so really high density to high distance. And this black line, that's the model. So if they were in a model of bats that don't care if they're near other bats or far from other bats, then you kind of get an equal distribution across these densities. But what they found in the actual data is this blue curve where they spend a lot of time at very short distances. So there's conspecific attraction. They hang out with other bats while they're flying around foraging. So that was one interesting pattern. But then the sort of the puzzle then comes in this plot. So in this plot, then they have the local density, your conspecific density. So you're alone, or you're with 1 to 4 bats, 5 to 8 bats, or 9 bats and above. And then based on where you are, so you can see like there's, this particular bat hung out with a lot of conspecifics here, a lot of red flags, was without conspecifics and so on. So they could try to see based on how often you're around conspecifics, then how often do you make an attack? And what they find is that when they're alone, they make tons of attacks on prey. But the instant they're near other conspecifics, they make very few to almost no attacks on other prey. And there is other evidence, which they go over in the paper, that suggests that there's interference effects, that when bats are very close to these other bats, they almost are focusing more on collision avoidance. There's a little bit of sensory confusion. They shift their attention away from their prey. And so they don't forage very well when they're very close to other bats. So that then raises the question, what explains, so we're looking for hypotheses here, what explains the high densities of these foraging bats, given the apparently high costs of foraging near other bats? So it seems like a surprise here that these two things don't seem to go together. And that's what this paper is trying to explain. So what they did to try to address that, any questions about these data, by the way? Right, so what they did to try to address that is they said, well, what if that we're going to hypothesize that there are these 3 different bat foraging behaviors, and we are going to test effectively the fitness prediction for each one of these hypotheses. And so you can say, well, we know that there's an interference effect. So we're going to say, imagine that bats are just trying to stay away from other bats. And then we say, well, there could also be an attraction effect. Well, imagine bats are trying to fly towards other bats and just stay near other bats. Or there could be a mixture of those two things where there's some benefit of being close to other bats, but some benefit for being away. But we're not modeling the benefit here. We're just modeling this motion rule where this is sort of the combined motion rule for all 3 of these things. You have the bat in the center, and you've got a little circle on the outside of it for obstacle avoidance. And so if another bat comes into this little circle, then this bat moves away from it. And then then outside here, this is the eavesdropping circle. So if a bat shows up in this outer circle, then this bat stays near it. Because the thought is that maybe this bat is benefiting from the sonar emissions of the other bats. So a bat can have this, this auto communication, a self signal where you have a sonar, it bounces off a prey item and comes back. Well, if you send out a sonar, it bounces off a prey item, but then it goes back to another bat, it might give that other bat information about where that prey item is. So if you can be near other signalers, you might be able to sort of parasitize their foraging signals and have it benefit you. And so that might be the benefit of eavesdropping here. So how they did to sort of test these benefits is they said, well, we've got, these models up here basically have to do with whether you're paying attention to this outer circle, this inner circle, or both together. So the interference, you're only paying attention to when bats come into the inner circle. The eavesdropping, you're only paying attention to when bats are in the outer circle. And then these two, you're paying attention to both. So you're attracted to bats here, and you repel from bats here. And what they did is they took this simple model and they fed in a simulated environment this way, where you start bats off over here, and you have patchily, so now we know that term patch, you have patchily distributed food. So you have a bunch of, say, ants that are in this simulated area and a bunch of ants that are in this simulated area. So the bats don't know where those areas are, and most of the area is empty. So then you can then measure bats of with these different policies. How well do they do when it comes to actually finding prey? And so when they did that, then they got this diagram here. So up top, we have the simulated bats that were repulsion only. So whenever a bat was really close to them, they ran away from that bat. Otherwise, they didn't pay attention to those bats. And what they found with them, so what we're plotting here, the time to first prey detection. And this is normalized. That's why it goes from 0 to 1. But it's better for this to be low. So this is how long it takes for you to find your first prey item. And so what they're saying here is in our bats that were repelled from each other, then at these low densities, they had a lower time to first prey detection. But then as you got slightly higher densities, because they were so busy staying away from each other, then it made for an ineffective search. So if bats were operating under this rule, then you would expect that they would have the best foraging outcome to be at very low densities. So this density is on the x-axis here. So this would not predict the high densities that you see in nature. Now, almost as a null model, they've got, well, what if they were eavesdropping? They were just being really attracted to other bats. But they weren't ever repelling from those bats. And sort of as you might expect then what you find is as you get higher and higher densities, then the bats that are sticking together, they're flying towards each other, then they end up finding the prey much faster. So they're actually very effective at search. They're making use of this information when if one bat is lingering around an area, they suck all the other bats there to it. Because if this bat has found prey, then the other bats can use that prey. So they can kind of scrounge off of that find. But so this would predict that this density, that the optimal density, the density that bats would sort of settle into, would be really, really high. And we know from other evidence presented in the paper that once bats get sufficiently high density, then there are these interference effects. And so although this does move in the direction you'd expect for this model, it sort of validates the model. This isn't a realistic outcome because bats they're not in the high densities that we predicted from this one. So when you combine the two, you get this nice bend here where you get an eavesdropping portion where bats get closer together, but then the interference kicks in. So this suggests there's some intermediate density where if bats could manage to forage at this density down here, then they could find prey the fastest. Every individual in the group would actually be a much more effective forager. They're sort of using information emitted by other bats, but they're not at such high densities to cause a lot of interference. It's like the perfect balance. That's the prediction of this model. And so the authors suggest that there's these counterbalancing forces that are out there, and that maybe that's why you see such high densities in bats, and that they've got this selective pressure to both parasitize information from other bats while also not getting so dense that they end up being unable to find prey because they're just navigating all these bats all the time. That's kind of the idea here. But that doesn't answer the question so what density might we expect? Are we actually going to expect them to be at this density here? So before I get to that, are there any questions about this diagram or where this comes from? That just means that they took the longest time and they divided all the times by that. So this time up here, this strategy took, let's say, 50 minutes to find their first prey. So then they said, all right, so all of the strategies, I'm going to take however long it takes to find their first prey and divide by 50 minutes. So then it'll be a 1.0 if you take the very longest, and it'll be, 0.8 would mean you take 80% of the longest time. Mm-hmm. Well, what do you mean 40? Yeah, right, exactly. So yes, if whatever the one is, whatever that standard is, 80% of that. Yep. Mhm. So, so this is a nice story that suggests that maybe bats would sit at this density. But we've found that that's not when you set up these stories in these foraging models. That's not always realistic to assume that this is going to be where the group size that you're actually going to observe in nature. And you know, so so what group size might we expect in nature? So I've just added in this green line here, and that green line connects to the basically the foraging success you would get if you went alone. And so this green line is saying that if you're at zero density, so you're just flying alone for any of these strategies, then basically it takes however long this, whatever, 50 minutes or 45 minutes or something like that to find your first prey item. So I've just taken that and I've extended this all the way across here. Now, this relates to a famous problem that you often hear about in sustainability courses and some of our souls courses. I mean, I don't know if there's any, sometimes I have sustainability students in the room. I don't know if there are any right now. But if we expect that this is a good description of the benefits to different densities for bats, where might we predict the density in nature to be? Where would it stabilize off? Any guesses? How many people think that in nature you're going to find the bats here? So that would mean at this optimal density. All right, how many people think it's going to be higher than the optimal density? How many people think lower than the optimal density? Anybody who says higher, why do you say higher? It just feels like it should be higher? Well, let's look about it. So we'll hold that thought. So how many people have heard of the tragedy of the commons? All right. So this is going to relate to the non-human version of the tragedy of the commons. So this is an, social foraging kind of independently developed all this stuff that we see in human sustainability literature and so on, and collective action problems, whatever. It all has kind of been independently derived in non-human stuff, and it's exactly the same results. But we just kind of give them different narratives. We do the non-human story. So here's the human story over here. So tragedy of the commons as a reminder here. This is a problem with so-called open access resources or common pool resources. These are resources that they're what they call non-excludable, which means if you're using the resource, like you're fishing in a fishery, you can't keep anyone out. Someone else can come and they can join the fishery and start fishing in the fishery. And that's it. You can't, regardless of how that affects your benefit from using the fishery, you can't keep them out. That's non-excludable. And the other aspect of an open access or common pool resource is that it's rivalrous. And that just means that every time one more person uses the resource, it makes the experience a little less for everyone who's already using the resource. So this is like highways near rush hour. This is also a common pool resource where everybody can get on the highway, but as more people get on the highway, it slows the traffic down. So everyone who's using the highway now experiences a slower experience. So when you have these open access resources, these common pool resources, you often have the so-called tragedy of the commons. And what that looks like for a fishery, so fisheries usually sit, thinking about your kind of population dynamics here, without anyone fishing at a fishery is going to have a fish population that's going to sit at the carrying capacity for the population. It's going to sit at a point where the fish don't have any more food, and so they sit at some stable population where they're eating all the food available, and there's no food left to make any more fish. So reproduction is effectively shut off. There's just replacement. It's not a great place in terms of the health of a population to be sitting at carrying capacity. But the interesting thing that happens is you start fishing out of a fishery, you move things away from carrying capacity, and the reproduction rate starts going up in the fishery. So even though were stabilized at like 100 fish, once you start taking fish out of the fishery, now there's food available for the remaining fish to have more fish babies, and the population can grow. But if you're actively fishing, the population won't grow. You'll just have new fish, and then you'll pull them out. So you can come to some stable balance where the fish keep producing lots of new offspring fish, and you basically keep pulling them right out at the same rate, and you now can generate a lot of output. So when no one fishing, the fishery generates no output. No fish are leaving the system. But as you start fishing a little more, you can start generating lots of fish because you create room for reproduction to happen and for the population to grow again. By reducing the population size, you allow the population to grow, but as it starts trying to grow, those who are fishing are just skimming all of that new growth off. And it's like interest in a bank. It's like you're constantly pulling the interest out of the bank. The principal stays the same, but then you use the interest to pay your bills. That's what goes on in a fishery to a point. At some point, you meet the maximum sustainable yield of the fishery, and then it starts declining. It goes the other way. So this is the plot that you often see in these fishery-like systems. So on the x-axis are like the number of boats in the fishery, and the y-axis are, you can think of it as dollars. So the dollars gained from fishing is this U-shaped curve, and the dollars spent on boats is this line here. So as you put more and more boats in, you're spending money on boats, and you're pulling more fish out. As you pull more fish out, that will generate a faster reproduction rate, which will allow the fishery as a whole to generate lots of fish to sell. But eventually you reach a point, the maximum sustainable yield, where this can't continue. And if you continue to fish, so-called overfish, then you go from reducing the carrying capacity pressures to now making it harder for fish to find each other to reproduce at all. And then the reproduction rate goes the other way. And so that's why you get these U-shaped curves and a lot of things that are like a fishery. A lot of these renewable resources have these U-shaped curves. And this, if anyone can come to the fishery, if we're talking about the pond in Kiwanis Park or something like that, they've stocked it with fish. If anybody can come and fish in there, you don't have to pay for a license or whatever, then initially people are going to say, wow, that I can get fish for free out of the pond, so I'm going to go and fish there. And that's going to generate more fish, and more people are going to come in, and then they'll gradually be fishing more and more. Eventually, you get to this point here where everybody who's, these 5 people that are in the pond fishing, they're getting a lot of fish out. And I think this is great. This is optimal. I've never gotten more fish out of this pond until now. But people who aren't fishing know that they're getting a lot out of this pond, and so they then join. And then now it goes from getting, $25, a pop out to less and less and less than that, until eventually the benefit you get from selling fish ends up matching the costs you get across everyone trying to exploit the fishery. And the net benefit minus costs, where this crosses zero, goes to zero. So the tragedy of the commons is that because anyone can enter, and because the resource has a better output than going it alone, you're guaranteeing that the resource will be exploited to the point where it ultimately is no better than going it alone. So that's what happens with rush hour traffic. It becomes so congested that the 10 becomes just as fast as taking the side streets. That's the tragedy of the commons, is that this resource that theoretically could get you home faster is now not being any faster than any of the other resources you have available to you. The tragedy here is that if the individuals are doing what's best for them, but there's so many individuals that the collective action of all the individuals doing what's best for them guarantees that the resource that motivated them to join this resource ends up being depleted to having no value whatsoever. Tragedy of the commons. And that's exactly what we predict to happen in animal systems as well. So in this bat system, this is a pretty picture that might suggest that, oh, maybe bats will optimize and be in at these densities, this perfect density here that's perfect for every individual bat. But then you have to ask yourself, what keeps other bats out? If there's a group of I don't know, 10 bats, and they're all finding prey very fast, why not have the 11th bat join? And so the 11th bat joins, and it's still doing better than it would be doing on its own. So remember, lower is better. And then, but then that kind of ruins things a little bit for the 10 bats that were in there. So then, but then still, it's still better than the individual. But the 12th bat then sees it's better than the individual. They join, and it keeps riding this curve up. So we actually expect the group size to be over here. So basically, we're going to get groups that are so large that the total benefit is equal to the benefit of going it alone. And so that's the tragedy of the commons, animal style. It's this sort of frustrating prediction that although you could have groups that are doing better because there's no governance method to keep them at that size, you can't keep anything out, so you end up getting much larger group sizes. And that's basically social foraging theory. So that's what we're going to be talking about here, is that that we have these two. So in the economics literature, they have the so-called socially efficient group size. That's if you had a way to keep people out, you would say, okay, once you get enough people in that everybody is getting the optimal return, so the biggest difference between benefits and costs, then in that case, you would stop and you wouldn't let anybody else in. But because you can't stop people from coming in, then you have the so-called open access equilibrium. And that's this group size over here. So the economists call this socially efficient and open access. In social foraging, we often just call them G star and G hat, but it's the exact same idea. So here's the social foraging picture. This is a generic idea where you've got fitness on this axis and group size on this axis. And so you've got an animal that's going it alone. This is how much fitness they get. You can think of this as like normalized fitness. So this is the fitness of going it alone is at 1. And then so as you start adding animals to the group, there are some what we refer to as positive externalities. These are benefits of being around others, network effects. So there's a positive externality that means that if you're nearby someone else, then both of you get a benefit from being near each other. And that may increase your fitness from the individual to the group size 2 point. And then you get here to the this group size 3, and that's what we used to call our socially efficient equilibrium. So I'm just going to call it G star here, which was the intake maximizing group size. If you can manage to hold out every other animal, this is beneficial for everyone in the group. They're doing so much better than they would as individuals. But if you can't keep other animals out, then you just keep getting animals joining, taking advantage of these positive externalities, and themselves placing what we refer to as a negative externality on all the other animals already in the group. So their action creates negative consequences for others by exploiting the positive consequences the others are generating for them. The positive and negative externalities. So we expect this to keep going until eventually you get to the open access equilibrium, which the largest group, so the group size that we might observe here will end up being roughly providing the same fitness as going it alone. So in nature, we usually see group sizes in between these two. And what is the X factor? What keeps group sizes toward one side or the other? Those end up being behaviors that exclude animals from joining. So when animals have a lot of resource holding potential, then they can control this G star. So as if you have like a hierarchy, you can have like an animal that sort of becomes the master of a particular foraging area, and they can allow certain animals in. And if they have the ability to keep animals out, then they can hold this group size. But if there's no mechanism that allows for that, and animals keep coming in, then we tend to see group sizes closer to the open access equilibrium, this G hat here. And then variations of that then come in between. So these are what we generally expect from social foraging theory, something in between here. And it is just the tragedy of the commons, but in a different context. Questions about that? This general diagram. And so we're going to see data from different studies that looks like this general diagram. And yeah. That's a great question. So in a lot of these things, this is a conceptual framework that we use as a lens on which to look at animal behavior. As we'll see in the next example with these wolves, if you find a group size that doesn't make any sense through this lens, it raises interesting questions to sort of say what's special about this. So if we look at an animal population, if we look at we just watch a couple of birds foraging and we see birds foraging alone, and this is how many seeds they get alone. And then we see birds foraging in groups together, and then we measure how many seeds they get. Then in that experiment, it's very common to see that you'll get the same every individual bird, regardless if they're alone or in a group, gets the same number of seeds per minute. And you get group sizes that are usually close to this open access period, but maybe a little bit bigger or a little bit smaller. So they're going to be in between these two, or they're going to be over here at one. We would not expect to see them over here. Now, if you go to another animal system like these wolves I'm about to show, then kind of beating me to the punchline, wolf packs are way over here. And so for a while, people were puzzling as to what's going on with wolves. Wolves appear to be foraging at a point that is worse than going alone. So they're almost getting less fitness by foraging in these giant groups. And then they uncovered what was going on. So when you see something that doesn't fit this simple model, that identifies a really interesting question. That becomes your priority science. When everything kind of fits this model, it's not as interesting and it's maybe not as publishable. Same thing with things like Hamilton's rule. If you've heard about that, we'll talk about that in the last lecture of the class. If things fit these simple rules, then they almost become less interesting. We use these rules not to say all of nature follows these rules. We use these rules to identify aspects of nature that we don't yet understand. And that's a great segue into these wolves. So this is a picture of some wolves with this giant moose. And so you look at these really large prey items, these ungulates like these moose here, and it looks like for these giant prey items that you might need a large group to take this thing down. But it turns out that wolves alone are pretty good at taking down these things. So they basically just, they'll often grab onto a leg or more often grab onto a neck, and they'll just hang on and they won't let go. And the moose will be shaking them off. And they find that after these encounters, these wolves will have 6 broken ribs, huge amount of damage, but all things that they can recover from. But then, of course, they'll get the moose. They'll get this moose prey. And so it ends up not being a puzzle, and actually being surprising. It's not a puzzle as to why you might see a wolf taking down a moose alone. It's a puzzle saying, why would a moose tolerate any number of other wolves in its group? Because it can take down a moose alone. And then this moose is so large that any other wolves that join are basically free riders. So that becomes sort of an interesting problem. So when I first described that, it sounds like, well, we expect to see group sizes close to 1. And maybe sometimes you tolerate, but you're not going to get much of this improvement for having additional moose here or wolves here. So, but what's surprising is that when you do this analysis, so they went to Isle Royale, they watched a bunch of moose, a bunch of wolves. They end up doing these calculations. So these are real data on real attacks and real moose and so on, and real group sizes. And what they find is that when there's a pack of 1 or very close to 1, you can find this is how much meat they get per day. So you can draw that individual line over, and you find that there is a little bit of an improvement once you go to about 2 wolves. You can take that and get a little bit more meat per day. But once you go to about 3 wolves, it goes below the individual line. So you're getting less meat per day with 3 wolves. And what's crazy about that is most of these packs are way over here. You get these giant wolf packs that if you're just thinking about the wolves and the moose, you can't make sense of these data. And this is what I mean by using this as a lens. Like anybody who's familiar with this model, when you look at these data, it raises all sorts of red flags. You're like, there's interesting ecology going on here. We are missing something given this. Like this, some basic ideas from natural selection and so on predict this thing. This is way off of that prediction. So what's going on? And that's what they addressed in this paper. So what's going on? Questions about this diagram here. You see that this is sort of a real data version of that cartoon, but it's showing way bigger group sizes than you'd predict from that cartoon. Okay, so what's going on? Well, one of the things that they did, remember risk-sensitive foraging that we covered last time? They said, well, let's build a model that tries to account for the tremendous cost that a wolf pays by taking down one of these moose. And it ends up being a huge metabolic cost. And then let's think about the effect of not just the other moose or the other wolves, but the scavenger birds. Because what they find is that if you take down a big moose on your own, and there happen to be a lot of scavenger birds out there, you're sitting there with broken ribs, trying to eat this thing, and you can't defend off all these ravens that are coming down and picking this thing clean as you're trying to eat at this thing. But if you've got other wolves around you, those wolves eat the moose slower than the ravens do. They are not scavengers, and they're not pulling the meat away. So those other wolves that you let in actually slow down the rate at which you lose the moose. And the amount of meat you get back from that when you're worried about the scavenger birds is actually more with the moose pack than it is with the scavengers. And it turns out that the amount of meat that they're getting back from the moose just barely, it's very, very close to the amount of energy and metabolic resources they need to repair themselves after the attack. So they're living on a nice edge. So if having more wolves around is better off than having a bunch of ravens around, then they'll take the wolves over the ravens because the wolves are easier competitors, or they're less costly competitors than the ravens. And so what they built a little model capturing that. And so the white bars here, that means that's when they model no scavengers. So there's no ravens in this risk-sensitive foraging model. The hatched bars and the dark bars are scavengers with 2 kilograms a day scavenging and 10 kilograms a day scavenging, respectively. And then they've got the probability of an energetic shortfall. So you expend all this energy taking down the moose, and then you eat whatever you can find left. And then at what point do you actually not make enough energy out than you do in taking down the moose? And what they find is when there's no scavengers around, then you minimize your probability of shortfall at a group size of 2. But when there's scavengers around, it's so much worse to have the scavengers picking off the meat than it is to have other moose or wolves picking off the meat, that you get an optimal group size of anywhere between 10 and 18. So it minimizes your probability of having an energetic shortfall by reducing the rate at which meat is being stolen from you, and you'd rather have wolves stealing it from you than the scavengers, which you really just can't defend. So that was one model that supported this idea that if you go into an area with no carrion birds, you're going to get small group sizes. If you go into an area with lots of ravens, you'll get very, very large group sizes. That was one model, one hypothesis that predicted data that matched what they see in real life. Any questions about that one? Where I show you another hypothesis that predicts the same thing. All right, so this suggests that it's all about risk sensitivity. Um, so yeah, so that's best for no scavengers, best when there's scavengers. Now, an alternative hypothesis is that the moose behavior is selection is driving things based on rate of return, which kind of goes back to our original plot here. And so, but now let's include the rate of loss from scavengers in this plot here. And that's what they've got over here in this model. So they have here for large prey, if I can get my cursor back, there it is. Large prey like moose is in this top one, and then small prey like deer are in this bottom one. And each one of these lines are different losses due to scavengers. And so the triangular one at the top, that's this triangular one, that's this triangular one. And you can see all of these curves have a shape similar to this one. So you get a slight uptick as a wolf joins your pack, but eventually it goes the other way. What they show here is that for large moose, then at moderate loss to scavengers, you get small packs. But so it ends up being, if you take the I'll just go ahead here. So if you drew the individual line across here, you'd find for this level of scavengers and this level of scavengers, then you'd end up getting group sizes of like 2 or 3. But down here, then you find that once you get a lot of scavengers, then the individual line is like below basically all of the other returns. So this predicts that once you get beyond a critical amount of scavenger losses, then you predict really large group sizes. So you maximize your fitness in terms of rate of gain for large prey by tolerating extremely large pack sizes. But down here with these little prey, like these deer, the idea here is that it's so small that it's easier to defend across the carrion birds. And you find that for the deer, then you get small group sizes for all levels of carrion birds. So this hypothesis would predict that if you go into areas with carrion birds, when you see moose taking down small prey, it will be in small packs, but in large prey, it'll be in gigantic packs. And you can test for that. So you have two hypotheses explaining the possibility of extremely large packs. Now, like I said, you can build experiments to discriminate among those two hypotheses to see what's stronger here. Is it the risk-sensitive explanation or the rate maximization explanation? But if we back out, there's a higher level hypothesis that carrion birds, scavengers, are driving group sizes. And we have two explanations that when you add carrion birds, that's the key factor that produces group sizes that are much larger than you can get if you don't include the effect of carrion birds. So it provides a lot of support that scavengers may drive for large group sizes. It's a little bit like talking about, cooperation is easier to get when you have outgroups that are threatening the group. So when you have these outside threats, you see much larger and more complex social structures than when you don't have those threats. Then you get things splintering off. All right, so questions about that idea that scavengers can lead to large group sizes. And I think, people have seen similar things in hyenas, for example. So, that's whenever you sort of add scavengers that can very efficiently steal a prey item from you, then it's beneficial to have others around you that eat slowly because they keep the scavengers away. Okay. All right. So, just in general, if you've got these big prey, it's an opportunity for the scavengers, which means it sets up these new opportunities for large group sizes. Okay. Questions about any of that? Okay. All right. So, yep, sorry. Scavengers. when there's more scavengers, there's more losses. There's more losses of your kill to your scavengers. And so if you've taken down a large prey, you've created a liability because that large prey, especially if you're damaged from the process of taking it down, you're trying to consume this giant prey item in place. And the rest of that prey item is out there. And so it's easy for these ravens to sneak in there and start picking away at that prey. So, you can get almost the whole prey item just, stolen from you by these murder of crows or ravens. Um, but if you can get other wolves around, they can't pull things away as quickly as these scavengers do. So then you've got a giant group of wolves around, and they're effectively building a wall that prevents the scavengers from coming in. So you're effectively paying a protection cost to you say I know that I took down this prey item. I paid a huge cost to take down this prey item, and you're freeloading, but I'm going to tolerate your freeloading. So I'm effectively paying you. They are paying the other wolves in meat in order to save the meat that they need. So, and that was kind of the risk sensitive idea there. It's like in order for them to guarantee that they're going to get enough meat to survive the night after expending that huge cost, then they're willing to pay little bits of meat that they're not going to eat to other wolves to be able to keep the birds away. And that protection cost, helps them survive. But if they didn't pay it, the scavengers would come in and they could eat so much of it that it would prevent the wolf that took it down from eating enough to make up the energetic cost of taking that moose down. So, foraging economics. Okay. All right. So then that lets us then zoom in to that group. So if you're talking about a group of animals that one of them has found the food and others just are waiting for the food to be found for them to share the food, how do you decide whether you're the one that's finding the food or sharing the food? How does that work? How can we explain the patterns that we see? And we're going to switch to a different model system for that. So this is a scaly-breasted munia, used to be called a spice finch, a nutmeg mannequin, if you were to go into the pet stores to find these. And so this example here is you can set up in the lab a grid of these little cells. And so each one of these cells has a little cache of seeds in it or nothing. So they search around this grid looking for seeds, sticking their little beaks down into these cells. And then they, so you notice some birds seem to be just searching and other birds seem to be moving towards other birds. So there's a big group of birds here. Occasionally you'll see a bird run like that one and join another bird. So you see some birds that are looking down a lot and some birds that are joining other birds a lot. And it turns out that you can quantify this. And so you can look at an experiment like that and you can put an automated system so you can watch the sides of these bird heads and you can then calculate the angle at which they're looking. So you can kind of connect the dot between their eye and their beak, and you can figure out, are they looking up or are they looking down? And the looking down cases here, then for these types of birds, for birds that are in this state looking down, then as you see them hopping around, they will find more and more patches. And those that have their head looking up, then as the proportion of time they spend with their head up directly predicts the proportion of patches they join after another bird has found it. So they view this as a visible way to tell the difference between a so-called producer, one that is finding prey or finding these seed items, and a scrounger, one that is kleptoparasitizing, one that is stealing prey from the producer, joining these groups. So this one here explores the environment to find food for itself. It's a private good. But because it can be observed, because of the eavesdropping, it creates a positive externality for this group. This group can then use that when it's looking up for these birds, it's not finding any food. So if you're 100% scroungers, if there's no producers in the arena, no one eats because they all just look at each other. No one's looking down. So But if they can see the other producers, then that allows them to find food by stealing it from the other producers. That creates a negative externality on the producers. So the producers are creating a benefit for the scroungers are creating a cost for the producers. And so the real question is, how frequently, if you put a bunch of birds in one of those experiments, how frequently would you expect to see producers and scroungers? Can we predict accurately that we're going to see for these 10 birds that consistently will have 2 producers and 8 scroungers? And what are the variables that determine that? That's the problem. So any questions about this problem? These 2 social states. Am I looking for food or am I looking at others? Okay. So there is this little model that they build called the producer scrounger game. So the map here, it might look like a lot, but there's not a whole lot here. You can use the speed of the bird to figure out the encounter rate with each one of these patches. So how many patches are out there? This is similar to that A value that we had in Holling's disk equation. So if this is like patches per second that a producer can find, and this is the length of the experiment. So let's say this is a 10-minute experiment, or I'll just make it easier. Let's just say it's a 10-minute experiment, and let's say this is patches per minute. So if it's like 1 patch per minute times 10 minutes, on average, we'd expect them to find 10 patches during the experiment. So this is saying how many patches do you find during the experiment? And then this is how much food they get out of each patch. So we're assuming the producer gets immediate access to the patch, so they get what's called a finder's advantage. So if there's 10 seeds in there, then maybe they get the first 2 seeds before anyone rushes over and tries to steal from them. So this is how much they're guaranteed. Everything else, so F is the total number of seeds in the patch. This is everything that the producer doesn't get in the finder's advantage. And that gets divided equally among the finder and everyone else, and the scroungers. So if G is the total number of birds in the arena, and if P is the proportion who are producers, then 1 minus P are the scroungers. So this is how many scroungers are there. So you're dividing all of the other seeds by the number of scroungers in the arena plus 1 for the producer. And so this is what we model as the producer's intake rate, the number of seeds the producer gets over the experiment. So in order for us to predict the number of producers and scroungers, we now need to do that with the scroungers. But any questions about this? And that all of those descriptions are summarized over here as well. Questions about that expression? Okay. So then the scrounger, what does the scrounger look like? Well, it's very similar, but they have no finder's advantage. Otherwise, this is identical to that up here. And this is the number of food patches found by all other producers in the arena. So it's basically just, you assume there's this, every producer finds this many patches, but how many producers are there? Well, it's P proportion times G group size. And so this is the total number of patches found by producers. So if you're a scrounger, these are all of the opportunities you have to steal food. And so every time one of those pops up, then you run over to it and you get a share of whatever's left over after the producer takes their finder's advantage. So we've got these 2 cost functions here, or these 2 benefits, these 2 intake rates. And they depend on the proportion of producers. So we can now we can try to predict how many producers we'd expect at equilibrium as these birds sort of say, I haven't found things very often, so I might switch to a scrounger and see if anyone else has found things. Or they might say, I haven't seen anyone find things, so I better switch to a producer so I can start finding things. So how might that work? All right, so any questions about these intake rates where we graph them and then show where we would predict the groups to settle out? Okay. So if you plot these things, you get these 2 lines. I'm plotting against the proportion scrounger, just for convenience from the shapes of these plots. So this is the payoff to a scrounger, the dark line. And this is the payoff to a producer, the light line. And so as you get more scroungers, it becomes less beneficial to be a scrounger and more beneficial to be a producer. So we get these two regions. We get a region of scrounger growth. So in this region, the dark line, which is the scrounger payoff, is higher than the light line, which is the producer payoff. So it's better to be a scrounger. So you start scrounging. You stop looking for seeds. You're just looking for birds that are looking for seeds. And the proportion scrounger moves to the right. Now, if you go too far, then you're in this region where now the benefit to being a producer is better than the benefit to being a scrounger. So it sounds like the scroungers always like got the better job because they don't have to do any work. They just have to steal the food. But if there are a lot of producers and very few, so in this case, we've got a higher intake rate of the producers. So what we're saying here is that if the producers are really good at finding the food, then it might not pay off. Or if there's very few, I guess that's what I should say. If there's very few producers out there, then being a scrounger is not very good because you don't see many opportunities to steal. So it's actually better to switch to being a producer. And that's what we have here. So this is the region of producer growth. At this point, there are so few producers that being a scrounger is a losing strategy. So you end up getting fewer scroungers. So things move back here. And things stabilize at this point where the benefit to being a producer is equal to the benefit of being a scrounger. So you can predict, if you know all of these terms, and like we'll see, you can set these terms in the laboratory. If you know all of these terms, so you know how many seeds you put in each patch, you know how many seeds a producer gets when they find it, you know the group size. If you know those three things, you can predict what fraction of the group size will play producer, will be the ones looking for seeds, and everyone else will be looking for producers. That's the idea here. And it's not better to be one or the other. They balance out. It is identical in value to being a producer as it is to being a scrounger. Neither is doing better. They both are getting the same amount of food per unit time. Okay. So that's how we solve for that. And we're going to look to see if that works. But any questions about this idea that we just set one social strategy's payoff equal to the other social strategy, and we found the point, the mixture of the two that balances those two, just like we did with the tragedy of the commons, where you join the group until the benefit to joining matches the benefit to not joining, and then at that point the group sizes stop growing. It's a similar idea here. Okay. We often use this to just mean that's the optimal amount. So this is the P without the asterisk, just represents the proportion that is currently a producer. P star means the predicted fraction of the population that we would expect if the producers and scroungers were both trying to maximize their intake rates. So it's the optimal behavior. It's the predicted behavior for the group. And this is not a group level property. This is both producers and scroungers trying to maximize their intake rate, and they just level out that you're going to get 2 producers and 8 scroungers, and they're all 10 birds individually are going to be doing the same. Okay, so let's see if it works. So they set up this nice little experiment. So you've got they put 6 birds or so on, or however many birds inside this arena. There's a wall that is a half-height wall that goes across this arena. And it has a producer side and a scrounger side. The birds can choose to be on whichever side they want. They just have to jump over the wall. If you jump over to the producer side and land on this perch, you can pull a string. And when you pull that string, a certain number of seeds get dropped right in front of you. So you're the only ones have access to them. But another set of seeds gets dropped into this collecting dish on the scrounger side, where you still, if you're fast enough, can get over the wall and get and eat those seeds. But others that are on this side can also get quick access to them. So this experiment is built so that they can set that finder's advantage. So however many seeds drop onto the perch side, that's A, the finder's advantage. And the total number of seeds, that's however many seeds are kind of dropped into this tray or the finder's advantage together. So you can set both of that. You can set how many total seeds per patch and how many go to the finder. So you can set both of those, and you can set the number of birds because you put how many birds are in there. This allows you to test whether that formula predicts what you end up getting out of these groups. So what happens? So these are three different flocks. So these are all different individuals. So this is one group of individuals, is another group, and another group here. And what they've done is they've started out in all three of these replications of the experiment, configuring the number of seeds to predict that you should have one scrounger initially. So they adjust the things. So that formula, that P star formula, is such that everybody's a producer except for one bird. And what do they find? Initially, birds start out doing both strategies, but then they decline, and then eventually they are within a confidence interval of the prediction of one scrounger. So they do exactly what's predicted. Then, right in the middle of this experiment, they reconfigure that experiment so that now there's a different number of seeds being dropped on both sides, so that the new prediction is going to be roughly 2 to 3 scroungers in this bottom half of the experiment. And right after they make that change in all three flocks, they then adjust, and now you have 2 to 3 scroungers. And this happens across those three flocks. So it seems to be working. It seems to be that the birds are trying to maximize their intake rate of seeds, and all of the birds are doing that simultaneously. But there's two ways to do that, either by looking for seeds or by looking for birds looking for seeds. And they switch which one of those they do in order to best, whatever's best for them at the time. So if they're currently scrounging and they're not getting any seeds, they start searching. They're currently searching, and there are others searching. So there's others finding all of the seeds, then they start scrounging. And it ends up leveling off with the predictions. Any questions about this experiment? So clear what they've done here and how they set this up. Okay, so what's amazing about this too is that you can take those birds you put in the experiment. So you take those 6 birds and you can label them. And you find the birds are pretty consistently that one bird will be a producer, the other bird will be a scrounger, and so on. So you can label them by producer or scrounger. You can put them away in separate cages in the experimental, in the area where you take care of all the animals, and you can wait 6 months and put them back in the experiment after 6 months. And the same birds who used to be a scrounger still are scroungers. The same birds that used to be producers still are producers. So it's almost as if they've got this sort of predisposition to be producers or scroungers, which maybe isn't so surprising. But what's really fascinating about it is then you can say, well, what happens if we take one of these birds? So we're going to take these 6 birds that were together, and we're going to take one of them and swap it out with a totally new bird that has never been in this group before. When you do that, it changes all of their identities. So I swap in a new bird, it's looking the other direction, and you get a totally different mix. The ratio of producer to scrounger is the same, but it really shows that who ends up settling out as a producer or a scrounger depends on who's there. So it's like when you go into a meeting and everybody is like playing a certain role, like you're sitting around the table or something like that, and one person swaps out for someone else, and it's like everybody, the whole dynamic in the room changes. That's what you're kind of seeing right here, is that, when you swap in this one bird, it's a little faster at this, it's a little slower at this, it's able to, it just changes things, these micro scale things that aren't in the model. And it just changes, again, the distribution has to be the same because that balances the rates. But the identities of who does what, then it depends upon these birds here. So it's this interesting emergent property. Questions about that? Is that clear? So the producer scrounger game. So we use that game to model all sorts of similar relationships among social foragers, where you've got one that's doing sort of the exploration work and another that's kind of doing the exploitation of the explorer's work. Okay. And that is kind of our survey of, it's how we get started. We're going to talk more about cooperation and competition. So we talked about exploitation primarily today. We're going to talk about cooperation and competition on Thursday. Big things I want you to take away. It's great if you pick up these terms, positive externality, negative externality, and are able to tie social foraging to the tragedy of the commons. This idea of a socially efficient equilibrium that you almost never hit, and instead the open access equilibrium that animals and non-human animals, and humans, I should say, both end up being described by this open access equilibrium. And then this idea of a producer-scrounger game. And I didn't talk about these, they're on the slides, but I didn't highlight them, so I'm going to highlight them here. This idea that you stabilize at a particular frequency of behaviors, like 20% producer, 80% scrounger. We refer to that as the SEF, the stable equilibrium frequency. And this idea that you can change your behavior dynamically and eventually you settle out at the stable equilibrium frequency, we refer to as a behaviorally stable strategy. So it's a strategy that can achieve stability over behavioral timescales. In other classes, you might have heard of an evolutionarily stable strategy. That's a strategy over generations that settles out. This is over life history or even over very short time periods. You can switch from one behavior to another. So it's a little closer to learning than evolution. And that's why we give it a special name of BSS instead of ESS. So, all right. Any questions about any of those things? The takeaways? If not, then we can get you out a little early. Yeah, oh, well, question? Producer scrounger is the bird example we have. Yep. You could also, we do talk about producer and scrounger in other animals, but those particular finches or those particular nutmeg manakins are model systems for studying producer scrounger. Okay. So attendance for today, we'll do a short answer. If I can get the poll up. And question is, what type of externality is generated by a producer openly searching for food? So if a producer is just walking around in the open looking for food, it is generating an effect on others. What type of externality is it? So basically, there's one of two words you could choose there. So positive or negative. And that's all I've got for you. So we'll see you for the conclusion of social foraging on Thursday.